Hello everybody, I'll give it a minute, then I'll start on this topic, which is practical applications of differentiation. Right, so I hope you're all well. Decided to do quite a challenging topic tonight. I think practical applications of differentiation is one of the topics in first year maths that students find probably one of the most difficult aside from mechanics and logarithms. So let's make a start. So as always, start with a few notes. And just write this down. So differentiation can be used to solve real life problems that involve maximizing or minimizing quantities. Such problems are called, in a key bit of terminology here, optimization problems. So you might see them referred to as optimization problems on the exam. So just do me a favour, just tell me that my current stream's audio bitrate is below the recommended amount. Can you type something in the chat, please, just to make sure that you can hear me? Yep, brilliant. Thank you very much. That's great. False alarm. So we're going to solve some optimization problems now. And they start off relatively straightforward. Brilliant. Thank you all. Thank you very much. So they start off pretty straightforward, but we're going to get more and more tricky ones as we go. So there's one there. So it says the volume V of a box of height x centimetres is given by that there. V equals 4x, 5 minus x squared, where it tells us that x is restricted to be from 0 to 5 exclusively. So it can't be 0, can't be 5. Find dv by dx. Well, with this, the first thing we should do, we're not ready to differentiate it yet. First of all, we need to multiply out the brackets. So let's do that now. So part A, V equals 4x. Let's multiply out those brackets. 5 minus x squared is 25 minus 10x plus x squared, which in turn is equal to 100x minus 40x squared plus 4x cubed. And now we are ready to differentiate. We've got it as a nice single inline expression, no brackets or anything like that. We are ready to differentiate. Now you probably remember the differential being called dy by dx when the equation is something like that, y equals x squared plus 2x plus 3, for example. But now that the variables are v and x, the differential is now called dv by dx, no longer dy by dx. Again, that initially confuses a lot of people. So dv by dx is equal to 100. So remember, to differentiate, you times by the power, take 1 from the power. So that power there isn't written, it's actually power of 1. If we times by 1, then take 1 from the power, we get 100x to the 0, which is just 100. Here, times by the power, we get 80x. Take 1 from the power, 80x to the power of 1. Plus, well, times by the power, we get 12x. Take 1 from the power squared. And there we have it. We found dv by dx as required by the first part of this question. Part B, the trickier part. Hence find the maximum volume of the box. Well, to find a maximum or minimum for any curve, and think of this just as a curve where there's an x-axis and a v-axis, not x and y, but think of it as x and v. So to find the maximum or minimum of any curve, we differentiate. Luckily, we've already done that. And then set the differential to 0. And the reason we do that is because in any curve, a maximum or minimum occurs when the gradient is 0 and dv by dx is the gradient. So we want where the gradient, 100 minus 80x plus 12x squared equals 0. Now in a question that says show full working or show detailed reasoning, as some of the exam boards say, you might be expected, or you would be expected to show full working, so show yourself factorising or using the quadratic formula. Luckily, that's not the case here. Luckily, we've got a calculator that'll do the job for us, so we don't even need to go into factorising. We can just let our calculator solve the problem for us, and that's encouraged at A level. If it doesn't say show full working, don't feel any pressure to. So, going for a polynomial of degree 2. And the x squared term we can see is 12. The x term is minus 80. And the constant term on its own is plus 100. Let's see what that gives us. So that gives us x equals 5. Or, with it being quadratic, we could get another one. X equals 5/3. So 2 potential answers. Now one of these we can discard instantly. I'll let you type in the chat which one we should discard. So which one's the bad answer here? 5 or 5/3, type it in the chat. Bit of a delay, so I won't get it for a little while. But we mathematicians love awkward silences. Yeah, we get rid of 5. 5 is the bad answer. And the reason that 5 is the bad answer is because of that there. It's telling us that x can't be 5. So if we cross that out, but when we cross an answer out, and here's an exam tip, a tip for getting marks in exams, always say why you've crossed it out. So just annotate it, because of that. Therefore x equals 5/3 is our answer. So we haven't finished yet though, because it asked us to find the volume. We found the x value that gives the volume currently. So let's actually find the maximum volume of the box now. So therefore v equals, and we've got the formula right at the start for that, so it's 4x. So 4x 5 minus x squared. So putting that in the calculator, 4 lots of 5/3. 5 minus 5/3 squared equals 2000 over 27. Because it's a practical problem and it didn't ask for an exact value, probably should give a more user-friendly answer as well. Let's go for 74.07. Like that. So, final part, and this is one of the things that it can do to catch you out in an exam. So it's to use calculus to justify that the volume you found in part B is a maximum. For that, to justify whether something's a maximum or minimum, what we need to do is find the second differential. So d2v by dx squared, as it's pronounced. So d2v, don't know why they call it d2v by dx squared, why one of them will say 2, the other will say squared, but that's just what we call it. So we're going to differentiate this here, dv by dx, again. So the first one, 100 differentiates to 0, minus 80x to the 1 differentiates to minus 80, plus 24x. So there's our second differential, and we want to find out whether that's positive or negative for x equals 5/3 there. So positive or negative for x equals 5/3. So let's see. So let x equal 5/3, which implies that d2v by dx squared equals minus 80 plus 24 lots of 5/3. Let's see the value of that. Minus 80 plus 24 lots of 5/3. Which is minus 40. And again, these are the key parts that you need to incorporate in your answer if you're going to get the marks. So first of all, show that you've calculated the value. It's not obvious that that's negative until you actually write down the answer. But you've also got to compare it to 0, which is less than 0. Therefore, a maximum. And this is a key feature to put in your answer and a conclusion. Anything that says justify or show that a conclusion is appropriate. So I want to make things a little bit more difficult now. And if you have any questions at any point, feel free just to put them in the chat. More than happy to be interrupted. So let's try this one here. And this one's more difficult because we're not actually given the formulae that we need. We've got to make them ourselves. So this is only part 1 for now. So it says figure 10 shows a solid cuboid with square base of side x centimetres and height h centimetres. Its volume is 120 centimetres cubed. That's a key thing we're being given there. Its volume is 120 centimetres cubed. So what I would do before I even read on, I would try and get that information in mathematics on paper. So the volume is 120. So let's find the volume in algebra. So the volume is cross-sectional area, so x squared times the height. So what that's actually telling us is that x squared h equals 120. And we'll come back to that bit in a moment. That's probably going to be, well, almost certainly going to be useful later. So part 1, find h in terms of x. Hence show that the surface area, a centimetres squared of the cuboid, is given by that formula there. Well, what we've just done there, the thing we've just written, will help us fulfill this part here. Find h in terms of x. Because here, this formula now gives us something we can rearrange to get h in terms of x. So part 1, x squared h equals 120 implies that h equals 120 over x squared. So that's that bit done. We've found h in terms of x. Hence show that the surface area, a centimetres squared of the cuboid, is given by that. So all 6 faces here have a certain area. 4 of them are the same, 2 of them are different. Can you go about now writing an expression for the surface area of that cuboid in terms of x and h? Then once you've done that, we notice that there's no h's in this, where we can eliminate h using that. So I'm going to take a step back for a couple of minutes. I'm going to let you try and finish that part off. So the area is 4 lots of the tall side, 4 lots of xh, then there's 2 squares, top and the bottom, plus 2 x squared, equals, well here we can see it wants the 2x squared first, so we'll put that first, plus 4x, and we know what h is equal to now, it's 120 over x squared, which is equal to 2x squared plus 480 over x, as we were required to show. So just a little conclusion, therefore the surface area A equals 2x squared plus 480 over x. So part 2, as with all these optimization questions, we're probably at some point, almost certainly at some point, going to be asked to differentiate. So it's asking us to find dA by dx and d2a by dx squared. Go for it. Right, so currently it's not yet ready to differentiate because 480 over x isn't in a differentiation friendly format. we need to write it as a equals 2x squared plus, and the way I decide what to write, first of all, I cover up the x to see that the number needs to be 480. Then I cover up the number to see over x. Well, over x, the reciprocal of x is x to the minus 1. So that seemed probably a bit more obvious there, but an example where it's not so obvious, what if it was 3 over 2x that we're being asked to differentiate, for example? Well, the strategy, cover up the x to get the number, 3 over 2. Cover up the number to get over x, x to the minus 1. So that's my two-step process for writing things in a differentiation-friendly format. Right, dA by dx now equals 4x minus 480 x to the power minus 2 times by the power, take 1 from the power. d2a by dx squared equals 4 times by the power, take 1 from the power, minus, double minus rather, which makes it a plus, 960 x to the minus 3. So we've done that. Finally, part 3. So learn from what we did before, hence find the value of x, which gives the maximum surface area. So there's that part of the question there. So remember what we did. We set the differential to 0 to find the stationary point. And because it's asked us, asked us to calculate d2a by dx squared, even though it hasn't explicitly asked us to prove that it's a minimum using the second differential, it would probably be safe to, just in case that's what they want. So even though it hasn't explicitly asked, play it safe. So I'll quietly get on with this alongside you, and you can check your answer against mine at the end. So I've got that value for x there. Which covers this part of the question. Hence find the value of x, which gives the minimum surface area. Find also the value of the surface area in this case. Okay. So sub that in. 145.973. But as I said, they've asked us to calculate the second differential in part 2, so whilst they haven't directly asked us to prove that it's a minimum, we really ought to, just to be safe. There's 5 marks. It doesn't feel like we've done 5 marks worth of work yet. So I can tell you in the mark scheme, actually, for this, they do want you to find the minimum, to prove that it's a minimum, even though they don't ask, which in my opinion makes it a bad exam question. However, context, 5 marks, and the fact that in the previous part we worked out the second differential, it is always a safe bet. So, let x equals the cube root of 120 again, which means that the second differential, d2a by dx squared, equals 4 plus 960 cube root of 120 to the minus 3. Let's work that out. 4 plus 960 cube root of 120 the power of minus 3 which is 12. And remember, bigger than 0, always compare to 0, then conclude, therefore minimum. So that's that one. Right, let's go for another one. So actually, I'll do this piece by piece. I'll give you that bit first to do. We'll put the other bits on as we go. So a solid glass cylinder, which is used in an expensive laser amplifier, has a volume of 75 pi centimeters cubed. Remember, stop reading at this point and write down something in maths to do with a cylinder and having volume 75 pi centimeters cubed. That's probably going to be useful later. So the trick here is you've got to make the formulae yourself. Might help even draw a diagram. So there's our cylinder. Bit rubbish. Radius. Height. Therefore, that piece of information there, the volume of 75 pi, the volume is pi r squared h of a cylinder. And we're told that that's equal to 75 pi. There we go, we've written that down in maths. Then it says the cost of polishing the surface area of this glass cylinder is £2 per centimetres squared for the curved surface area. £2 per centimetre squared for the curved surface area. There it is. And £3 per centimetre squared for the circular top and base areas, just there. Given that the radius of the cylinder is r, lucky guess at the letter that we're going to use, show that the cost of polishing, C, is given by that. Right, so, first of all, we've got 2 circles, top and bottom. In fact, you know what? I'm going to give you a moment. I'm going to give you a moment to do this. I'm going to hold back. You could probably do with the satisfaction of doing some of this completely by yourself. So I'll give you a couple of minutes, then I'll take over. Right, so my logic for this, so the cost is going to be equal to, so you've got the base and the top, which is pi r squared, and there's two of them, and these cost £3, so that's that first term. Then the curved surface area, which is h, times the circumference, gives us that rectangle that wraps around the cylinder. H times 2 pi r, and that costs £2. So let's simplify that. Equals 6 pi r squared. I can see I've got that there. I'm looking to be along the right lines. Plus 4 pi r h. And notice there's an h to get rid of, but you learned how to do that in the previous example. So in that previous example, we already derived an equation given from the information in the question to be able to find what the thing we wanted rid of was. So let's do that. So I notice if I divide both sides by pi, like that, so r squared h equals 75 if I divide both sides by pi, which means that h equals 75 over r squared. And now what we can do, we can take that h and use that to eliminate that h there. Which is equal to 6 pi r squared plus 4 pi r times h, which is 75 over r squared. Therefore, you can simplify now. C equals 6 pi r squared. 4 times 75 is 300. So, plus 300. There's a pi there, and r over r squared gives r on the bottom. And there, we've shown what we were asked to show. Part B, which is going to appear now. Try again. There it is there. Use calculus, i.e. differentiation or integration. In this case, calculus refers to differentiation, to find the minimum cost of polishing, given your answer to the nearest pound. So I think they've tried to catch us out there. Remember that bit. That'll be something that catches loads of people out. So use calculus, i.e. differentiation. So again, I'll leave you to it for a short while. I'll let you deal with differentiating that and solving. Any ideas for the next topic we'll do? I've had some suggestion of stats or mechanics, but I'm still happy to go through pure. Just type it in the chat, by the way. While I'm waiting for you to have a go at this, just type something in the chat. Whatever topic you think I should do next. Yeah, integration's a good one. Yeah, I mean, probability is a very, very broad set of topics. So I'd happily do something on probability, but it would have to be a bit more specific. Binomial expansion and factorial notation, fair enough. Hypothesis testing, that's a good one. I absolutely love hypothesis testing, by the way. We'll definitely do that at some point. Before that, we'd have to do binomial distribution, though. So, that could be the next few weeks of lessons. Doesn't look like we're going to be back to school anytime soon. So, I think there'll be a few more of these sessions. The logarithm stuff I did last week. I think with logarithm graphs, it's not a big enough topic to take up one of these sessions. However, I've done a couple of YouTube videos on it that you can have a look at. So, anyway, right. So, use calculus to find the minimum cost of polishing. Give me your answer to the nearest pound. Right, so let's write this in a differentiation-friendly format. First, before we differentiate, so c equals 6 pi r squared plus 300 pi r to the minus 1. So now we'll find the minimum cost, so we're going to need to differentiate. So the variables are c and r, so dc by dr equals, then differentiate, we'll get 12 pi r minus 300 pi r to the minus 2, which is equal to 0 because it's a stationary point, in this case a minimum that we're finding. So that implies that, and let's go about solving it. So if we divide both sides by pi, we get 12r minus 300 r to the minus 2 equals 0. Times both sides by r squared, I get 12r cubed minus 300 equals 0, which means that r cubed equals 300 over 12 equals 25. So that means that r equals the cube root of 25 but we weren't asked to find r, we were asked to find the cost, c. So c equals, so let's shove it back in that formula there, equals 6 pi the cube root of 25 squared plus 300 pi the cube root of 25 to the minus 1 equals, and it wants it to the nearest pound, remember, so 6 pi cube root of 25 squared plus 300 pi cube root of 25 to the minus 1 equals 483.48, which is approximately equal to the nearest pound, 483 pounds. Like that. So that's that bit done. Then finally, last part, and you probably know what's coming here. Justify the answer is a minimum. So for that, we need to find the second differential. Not many marks for that. dc by dr equals 12 pi plus 600 r to the minus 3 so let r equal the cube root of 25 equals 12 pi, which implies 12 pi so Zane, you thought the first derivative gives you the gradient function. Right, so you're quite right to point that out. I have actually found the second derivative, but I've called it the wrong thing. I called it dc by dr there. What I really meant was d2c by dr squared. So I'm actually here differentiating that. And it's a common misconception when finding the minimum in part. So part B, we didn't need to find the second derivative. To find the minimum or maximum, we find the gradient function and set that equal to 0. And that's a really common misconception, and I'm glad this has happened. So to find the minimum itself or maximum, set the gradient function equal to 0 and solve. Then to justify whether it's a maximum or minimum, that's when the second differential comes in. First derivative gives the stationary point, second derivative verifying it's a maximum or minimum. But I'm glad you pointed that out, because this one here, I actually called the wrong thing. I called that dc by dr, when actually I'd already differentiated again, so it's actually called d2c by dr squared. So 12 pi plus 600, the cube root of 25 to the minus 3. So 12 pi plus 600 cube root of 25 the power of minus 3 equals 61.70, which is greater than 0, therefore a minimum. So again, this part tells you what the stationary point is. First derivative tells you what it is. Second derivative tells you whether it's a maximum or minimum. Let's try another. So figure 3 shows a flower bed. Its shape is a quarter of a circle of radius x meters with 2 equal rectangles attached along its radii, basically as described in the diagram. Each rectangle has length equal to x meters and width equal to y meters. Given that the area of the flower bed is 4 meters squared, that's where you should stop reading and write something in maths. You've been given that the area is 4 meters squared. So there's something you can do there. I'll give you a moment to have a go at that. So given that the area of the flower bed is 4 meters squared, so that's 2 xy's, and notice that that has to be x plus pi times radius squared, but it's a quarter of a circle, and we're told that that's equal to 4. So the next part, to get y on its own, I'm going to divide by 2x. So to get from this line to this line, I'm going to divide by 2x. I can see I need an 8x on the denominator, so if I divide by 2x, I'm going to get an 8x on the denominator. So that means that y plus, and if I divide by 2x, I get pi x on the top, the x, one of the x's cancels. In fact, if I leave the squared there and do that, so I'll do no cancellation for now so that the 8x stays on the bottom. Take everything over to the other side, which means that y equals 4 over 2x, take pi x squared over 8x, and I'm ready to combine these over the same denominator now. So if I times this one here, I want both to have a denominator of 8x, so I times both the bottom and the top by 4. I get equals 16 over 8x minus pi x squared over 8x. Both got the same denominator, so that makes 16 minus pi x squared over 8x as required. Part B. What I'll do, I'll bring a picture of I'll bring the diagram down as well. So that you can see, because it's going to refer to the perimeter. So there it is there. There's the diagram. Hence show that the perimeter, p meters, of the flower bed is given by that. So not wanting to patronise you, but remember to get all the perimeter done. Take a moment to do that yourselves again. So I can see we've got 4 Ys. See, we've got 2 X's. And 1/4 of a circumference. Almost. Long day plus 2 pi r over 4. Like that. And we know what y is equal to now. Equals 4 lots of our y, which is 16 minus pi x squared over 8x plus 2x plus then we've got 2 pi r, so 2 over 4 is 1/2 pi x, like that. And I'm seeing a lot of pi's in there, so these must cancel at some point. No problem, Harry. You take care. Glad it was useful. Equals. So let's multiply this out now. We've got nice separate expressions. I think it was deliberately awkward of the first part to ask us to combine it over a single denominator. So 4 times 16, the top is 64, minus 4 pi x squared over 8x. And we've got plus 2x plus 1/2 x. You're very welcome, Hanua. So 64 over 8x. Do it step by step. Minus 4 pi x squared over 8x. Plus 2x. Plus 1/2 x. Don't forget the pi there. Almost forgot to write the pi. So 64 divided by 8 is 8 over x. Take away 4 over 8 is 1/2. and x squared over x is just x. There's a pi, plus 2x plus 1/2 x pi. They disappear, giving 8 over x plus 2x as we required. Nasty bit of algebra, that. Part C now. So we've got concluding that P equals 8 over x plus 2x. Part C, use calculus to find the minimum value of P. You might find this useful, Hanu. If you haven't done differentiation yet, you might find this useful in a couple of weeks then. So by calculus, it means either differentiation or integration here. In this case, because of the context of the question, clearly it means differentiation. Go for it. Differentiate it. So P equals 8x to the minus 1 before we even differentiate, plus 2x, we're putting in a differentiation friendly format, which means that dp by dx equals minus 8x to the minus 2 plus 2, which at a stationary point it has gradient function equal to 0. So we're finding where the gradient function is equal to 0 to find the location of the stationary point. That means that 8x to the power of minus 2 equals 2, timesing both sides by x squared. I get 8 equals 2x squared, which means that x squared equals 4. So in turn, x equals plus or minus 2. And x has to be equal to 2, since x is a measurement. It cannot be negative. So now I've found the value of x that gives that particular value of P. Let x equal 2, which means that P is 8 lots of 2 to the minus 1 plus 2 lots of 2 equals 4 plus 4, which is 8 centimetres. Double check on the unit just to make sure. No, actually the units were meters. Shame to lose a mark that late on without checking the answer. There we go, 8 meters. Notice though, no reference to the second differential here, nor has it asked us to justify. Therefore, I think we can safely say we're done. So I hope you found that useful. Hopefully you've learned a bit from that, and hopefully it's made what is quite a complicated topic a little bit easier. There were a couple of algebraic errors in the middle there, because the algebra at this level is so intense, but I hopefully that illustrates the need to keep checking your answers. We all make mistakes, and we just need to keep thoroughly checking over our algebra line by line to make sure that things haven't gone wrong. So checking is a really important skill as well. You're all very welcome. So next week we'll have, I'll take on board some of your suggestions, and we'll reconvene next week, Tuesday at 6 p.m. Glad you all enjoyed it.